Hello, my dear students, professionals. Welcome to this interesting video on aerospace engineering. So today we are going to discuss about the Tsiolkovsky rocket equation. So this equation plays a very important role in determining how much velocity can be gained, okay, by implementing certain stages. So this equation has been tremendously used by different space agencies, including our ISRO, NASA, in building the multi-stage or the thing or the different staged rockets to achieve the mission. Okay, the staging concepts comes from this sort of equation. Okay, so before going to the derivation, now let us understand what is basically this velocity gain. Okay, now let us consider a boy who is having a high load bag in his backpack. Okay, and he's running. Okay, he started running off. So while running he feels very much discomfort, and he tell me, hey, I'm tired, okay, of running. He used to tell me, okay, I'm tired of running. So after running so many hours, he started to find, okay, at certain point of time what he observed, like, okay, while running itself he started to throw his bag. Okay, so he's running and he's just throw his bag the backside. Okay, and now he is achieving some sort of velocity and he's very happy. Hey, I'm happy. Okay, he's telling, hey, I'm happy. So why he is happy? Because there is no more load on his back, and initially he is experiencing some sort of a tiredness because of the high load. Now he is not at all experiencing any sort of tiredness. Instead, he is getting an additional velocity which make him to run faster. Okay, so that additional velocity is called the velocity gain. Okay, so similar scenario is happening in rocket also. So if you have a different staged rockets, okay, now when it is the rocket is moving, and we have the fuel tank over here. So this fuel tank completes the entire consumption of the fuel, so this get wiped off. Okay, now we are remaining with the other two staged. Okay, now again this is getting consumed off. Now we are again remaining with this stage, and now again this is getting consumed off, and now we are left with the final stage. Okay, so that is the payload which is to be inserted onto the orbit. So this is called the staging phenomenon. So each and every point we are receiving some sort of a velocity gain. Okay, so this concept is being explained by the Russian scientist called Konstantin Tsiolkovsky, and his equation is very famous, one of the most favorite equations for all the aerospace scientists, engineers, and students. So in different textbooks, they have mentioned a complex way of solving it, but now by understanding the concept, we can derive it a very simpler way. So this will be very much relevant for professionals and the undergraduate students, those who are pursuing their aeronautical and aerospace engineering. Okay, so without wasting much time, let's get started. Now we draw a rocket structure. Let's say we have a rocket like this, having a mass. Okay, and it's moving in this direction. Let's say this is the direction of movement, forward direction. We have your mass here, we have velocity here, maybe at a time of t. Okay, fine. Now for a certain increment of time, okay, uh, there is a small mass which is being ejected out from the uh, rocket. Okay, that means this rocket structure doesn't require this mass again, so it is being ejected. So let's call this as delta m, which is a very small mass. And now we call this ejection velocity, which is called the V eject. In different textbooks, they have different terminologies or notations. So here we'll try to make the concept very simple. So we'll represent ejection velocity as v eject. Okay, and this is moving forward with a good velocity gain. Okay, so velocity gain is v plus delta v. Okay, and here the mass is a bit tricky because we have m from the parent. We have lost a child, that is delta m, so m minus of delta m. Okay, fine. So up to this much is very clear. Because a small mass being ejected delta m and we have ejection velocity v ejection, so we can say that the initial momentum experienced by this rocket may be for the time interval, let it be p of t, and the initial momentum for time of t plus delta t can be represented as p of t plus delta t. Okay, so up to this much is very clear. So p is nothing but the momentum for a time interval of t. Okay, so this is the momentum for a time interval of delta t. Okay, this is the final one, maybe this is the initial one. Okay, so here you need to consider we have the momentum for the ejection mass also, we have the momentum for the remaining mass also. Here we have the overall the total mass of the vehicle and the velocity. Okay, so this is one of the key thing we have to be very clear. Fine. So now let's do the change in momentum. So what will be the change in momentum? So change in momentum, okay, which is equal to the final momentum. Okay, final momentum minus of the initial momentum. Okay, now we have now let us solve the RHS term first. Okay, we have LHS, we have RHS. Now let's solve the RHS term first. We have m minus of delta m into v plus delta v, and now there is one more, an injection mass, which is basically delta m and v ejection velocity. Okay, v ejection velocity minus of the initial momentum, which is basically your m into v. So now here we should be very careful while performing the simplification. So this is a bit tricky. So we have m into v, okay, plus m times delta v. So this final so m terms we have done it over here, right? So mv plus m delta v. Now delta m into v minus of delta m delta v, okay, plus we have delta m into v ejection minus of m times v. Now this is very clear. So we can cross check once again. Mv, m delta v, okay, fine, it's good. Minus of delta m into v, okay, fine. Minus of delta m times delta v, okay, that is also good. Now we have the ejection mass delta m v ejection minus of mv. So this is basically the change in momentum principle we have already studied. So momentum is actually a property of any body or a moving body that can create some impact on other bodies. So that is the physical meaning of a momentum. Okay, mathematically we always refer it as, okay, we have a mass of m and we have a velocity of v. Okay, now so the product of mass times velocity will give me the momentum, which is again a function of kinetic energy. So there are a lot more to tell. So at this point of time, let's stick on to this derivation. So now we can cancel out the terms mv again. Okay, now you have, so here you should be very careful, delta m into delta v. So delta m is very small, delta v is also again small. A smaller times into smaller will lead to a bigger smaller quantity. Okay, now you can ignore this term. Okay, I no more require this term because this gentleman is very small. I don't want this. Now we have m into delta v minus delta mv plus delta m into v eject. Okay, now we can write this equation like this: m delta v plus delta m into v eject. Okay, I can put this into bracket, v eject minus of v. Okay, just I have done some rearrangement. Okay, I have taken delta m common and v eject minus of v. So v eject minus of v is nothing but delta v, because it is basically minus delta v. Okay, because always you have to remember, whenever we have a forward speed and now something is going to eject, okay, so that difference is nothing but delta v. Okay, so here you can see it is v eject of minus v, but here we can see it is v minus of v eject, so it is again a negative sign will come over here. Okay, so m into delta v plus delta m into, so here v eject minus v, here it is v eject, v minus of v eject, so definitely is going to be negative. So again there is no point of considering, because delta m is again small, delta v is again small. Now you neglect this term again. Now you get something called m into delta v. Okay, hope up to this much is very clear. Okay, now the change in momentum, as we have already seen, change in momentum is something just like p of t plus delta t minus of p of t, so which is equal to m into delta v. Okay, now we divide the LHS and RHS by delta t, because which is happening at a very small interval of time, so we apply the limit as well. So limit delta t tending to 0, which you have already studied in your +1 calculus. Okay, so hope you are remembering it. So, okay, so limit delta t tending to 0. So calculus is very important. When something is tending to something which is having a very low value, then ultimately this term is going to have a differential term. So this is something like dp divided by dt, which is equal to m into dv divided by dt. Okay, so this transformed to this term. Okay, because we have applied the limit on both sides, so I think this is much more clear. Now we just neglect these denominators we have, because it is happening at the same delta t time interval, dt time interval. So now here we have something more to consider, because p is basically your m times, okay, and you have the effective exhaust jet velocity of the rocket, which is considered as to be c. Okay, this is which is basically the jet velocity which has been experienced by the rocket. Okay, basically it is a function of the area, it can be a function of pressure. So this is basically something which can be determined with the help of thermodynamic and the area parameters. Okay, now here we'll take that as a constant with respect to mass, because we are dealing with mass terms. Okay, now we have d of mc, which is equal to again m here, m into dv. Okay, now c is a constant, so I'll put dm here, it is equal to m into dv. Okay, to this much is very clear. Fine, so c is basically the effective exhaust gas jet velocity of the rocket, d is a mass change, and m and dv. Okay, now I put a negative sign, because ultimately your rocket mass is getting changed. While liftoff or while launching, you can see that rocket will be having high amount of mass, but when it is going to the ocean, okay, till that phase your entire mass is gonna change. Okay, each time it is going to be decreased, because the fuel is getting consumed. Okay, everything is getting dispatched, so ultimately what is going to the ocean, it is nothing but the structural mass. Okay, so this negative sign is a bit relevant here, so I put a negative sign indicating that there is a decrease in the mass, okay, which is equal to m into dv. Okay, now in order to make this as a finite term, to remove the differentials, we need to get the total mass and the velocity gain. So what we do is like, I'll write over here, we have minus c dm, which is equal to m dv. Now I am integrating on both sides, minus c integral from initial mass mi to mf, okay, final mass dm, which is equal to m into integral of I can take this m this side, that will be good. Okay, I can take this m this side. Okay, now this will be from the velocity v, it has gained from v plus delta v. So delta v is actually a difference gain in the velocity, and now we can write like this. So ultimately we are getting something like minus c. This is dx by x integral the limits from maybe lower limit and upper limit. Now if you have studied, dx by x is log x, so log of, okay, log to the base e we can write, and we have a negative sign, so always put you can take this negative sign inside, so it will be coming mf divided by mi, okay, which is equal to delta v. Okay, so if you want to if you're having still confusion in this step, I can show for you, but it is bit it's bit basic, so you'll be able to know it. So integral dm by m is nothing like, okay, log of mf, okay, mf minus of log mi. Okay, so initially we have a minus sign, so it will be coming log of mi, okay, minus of log of mf. So I can write log of mi divided by mf, and now I can write again log of 1 by mf by mi. So this is how it has come like that. Okay, over here. Fine. So this is equal to delta v. So again I can write this equation very neatly. So here you can write c. I can write logarithm to the base of e is ln. So ln of 1 by mf divided by mi, which is equal to delta v. So again delta v is equal to c into ln of 1 by mr. So mr is a new term. This is called the mass ratio, which determines what is the final mass of the rocket divided by the initial mass of the rocket. Okay, so that is called as a mass ratio. We normally denote it by mr, and delta v is the velocity gain. Okay, now this is how the entire Tsiolkovsky equation works. So delta v is the velocity gain experienced by the rocket, and c is the effective exhaust gas velocity or the jet velocity of the rocket, and logarithm of 1 by mr. So this is our Tsiolkovsky rocket equation, and where mr is the mass ratio of the rocket. Okay, so this is how the equation has derived. So this is a very simple derivation, so probably you can have a look. Okay, and if at all you have any confusion, please let me know in the comment box. I will address you accordingly. So thank you so much, and have a great day ahead. Thank you.